Hi everyone, today I'll be presenting to you some preliminary results for an investigation into crash incidents data provided by the Victorian Government. Firstly, I will introduce the aims of this project. As mentioned before, this project focuses on the data provided by the Department of Transport and Planning of the Victorian Government, which provides statistics on crash incidents occurring in Victoria over the period of 2006 to 2020. This project aims to identify the most important features affecting the outcome of a crash incident. In order to do this, however, the project also needs to have a model that accurately predicts outcomes of a crash incident given related features. And finally, the project aims to provide avenues for future work in order to improve on any modeling deficiencies that were identified. Now I'll provide an overview of the crash data itself. It contains observations from over 200,000 drivers that were involved in crashes in the relevant period. 33 features were recorded about each driver and incident, which includes information on various aspects of the accident itself, as well as demographic data about the drivers and passengers and the vehicles that they were in. Notably, a majority of the features were categorical, with only 11 features being numerical. The target feature for this investigation is the severity of an accident, where Class 1 indicates that at least one fatality occurred, Class 2 means that at least one person was hospitalized, and Class 3 means only minor or no injuries were suffered as a result of the accident. Hence, this project is completing a classification task. Here, I'll present some preliminary models and results for classifying accidents and drivers to a certain severity class. I considered a naive classifier that was used as a benchmark, which simply predicts the most frequent severity class that it sees in the training set. For example, here we see that in the training, Class 3 was the most prevalent, and so for all future data, this classifier will predict Class 3 only. Next, a fully connected neural network, or FCNN, structure was investigated, which passes inputs through a sequence of dense layers of neurons, and each perform a weighted sum as well as a nonlinear transformation on its inputs before passing on to the next layer. Finally, a residual neural network, or RNN, structure was considered. Essentially, it allows inputs to take multiple paths through the network, either going through processing in the residual block, which in our case is just a small FCNN, or passing that section altogether via a skip connection before the results are added together and run through similar sections later on. This structure is intended to help facilitate efficient learning with deeper neural networks. Looking at the results thus far, if we only look at accuracy scores on the validation and test subsets, we see that the FCNN provides the best performance on average. However, with imbalanced datasets, a model could be simply guessing the majority class and ignoring classifying minority classes. The balanced accuracy score adjusts for this by computing accuracies within each class and then provides their average. Using this metric, we see that the RNN provides a much better performance on this front. Other than that, thanks for listening.